Welcome back. We're now going to be investigating our next section of mechanics, which is an investigation on why objects move. In the last two chapters, chapters 2 and 3, we looked at how they moved and be able to describe that motion, be able to describe the position and that change of position. Now in chapter 4, we're going to be investigating why they move. And we're going to focus on forces. And along those ways, we're going to talk about our laws of motion along the way. Now, we need to define what a force is. And we're going to just generically define force to be any push or any pull on an object. Okay? And then this is really crucial. I'm going to highlight it. Net force. We're going to be talking about net force a lot because you can have a force of push on an object. If I push on this screen, there's a force there, but it doesn't necessarily require as motion. Whereas a net force is considered to be the vector sum. So we're back to vectors. We have to be able to add up those vectors. So it's a vector sum of all the forces that are acting on that object. And the total force that it acts on an object during a specific time. That force can change as well. So again, highlighting or circling the vector sum of all forces. So we're going to have to recall how to add vectors. Now, this is kind of a summation. We said that force is any push or any pull on an object. And we can say that when a net force, so a vector sum, there is going to be a force acting on that object, a total force acting on it, that object will have a change in that velocity. And therefore, a net force will cause an acceleration. So whenever you have a net force, when F net is not equal to 0, because this is going to be something else we talk about later called equilibrium. When the net force is not equal to 0, then we get a delta V. We have to have a change in that velocity. Now, the units of force are called the newtons, named after Isaac Newton. We'll discuss that later on why. But a newton is the exact same thing as a kilogram times meters divided by seconds squared. And that's because of how we define it. 1 Newton of force, by our definition, will cause a 1 kilogram mass to accelerate at 1 meter per second squared. So obviously then a 2 Newton force causes 1 kilogram mass to travel at or accelerate at 2 meters per second squared. But that's going to be our definition. Now, this wasn't written down in a book somewhere. This is what a bunch of people got together and said, hey, this is what we're going to call 1 Newton. So this was decided upon. Now, there are 2 classes of force that we're going to look at this year. The first is called a contact force. And this is a force that exists because we come into contact with it. When I pick up this marker or this pen that I have in my hand, in order for me to exert a force in it, I have to come into contact with it. If I don't come into contact with it, I can't move it anymore. So if my hand's not touching it, it's not going to accelerate the way I want to. Okay? If I'm sitting on a chair, if that chair suddenly disappears, it's no longer going to exert a force on it. So it must involve physical contact. Okay, so we talk about must touch in order to get delta V. Okay? A field force, on the other hand, is a force, is a concept, is an idea. This is just actually a figment of our imagination. I shouldn't say figment of our imagination, but it's a concept that we came up with to explain forces that don't have contact. And the best one we've already talked about is this. If I drop this pen, there is a force acting on it, causing it to accelerate down. Now, for a long time, people try to say, well, there must be something touching it. There must be something pulling down. It must be attached to it, pulling it down. Eventually, we couldn't make that justified. We couldn't justify that in our heads or have explanation for it or evidence for it. So we came up with the idea of a field force. And this is a force that exerts forces across a distance or across a field. And so the best example of that is gravity. I mean, we have other ones as well. Magnetism, which we're going to talk about later. Electricity, we're going to talk about that later as well. Okay? And it turns out, kind of a sneak peek, spoiler alert, there's actually no such thing as a contact force. Even our contact forces are caused by field forces. But we'll talk about that later on this year. Now, because we talk about net forces, we need to know the vector sum of all forces. And there are many situations where there are multiple forces working on an object. It is often really a good idea to actually draw this as a vector diagram. And so I'm just going to give you an example. If I have a chair here, okay, it's a really bad chair, but we have somebody sitting on it. You can tell I'm a master of stick figures. Hang on, I've got to give them a little bit of a butt because apparently they weren't actually sitting on the chair. Or you can think of it a cushion. I don't care. Whatever makes you happy. Yeah, we'll make them happy. There. All right. Fantastic. Okay, they look awesome. Okay. But if that person is sitting in the chair, we know that gravity is pulling down on them. The force due to gravity is pulling down. But there's also going to be a force due to the chair pushing them back up. And the reason why I know this is because if that person sits in the chair, they're not having a change of velocity. They're just sitting there. If there's no change of velocity, there's no net force. So if gravity's pulling down, something else has to be pushing back up. So this is what we'll call a force diagram. Now, let's say we have somebody else come along and they're going to push that person. We'll put them in the evil red color. Oops. Their leg bent the wrong way. I apologize for that. Yeah, we're going to make them mean. And have some really bad hair. But let's say that they're pushing them along. Okay? So we'll put their force, I'll put that in the rainbow. They're pushing them forward. There's the force pushing. Now you notice I'm using subscripts here because I have now 3 forces. And so since I have to distinguish between them, I have to put them out this. Okay, so this is what's called a force diagram. I've drawn my picture, I've drawn my person, I've drawn all the forces acting on them. Okay, another way that we can do that, again, if you're kind of like me, you don't have the world's best artistic ability, the other way you can do this is what's called a free body diagram, where we get rid of the diagrams and we replace the person with a dot. And so here's my force due to gravity. Here's my force due to the chair. Oops, wrong color. And here's my force due to the push. Now, this is the exact same thing as our other diagram. It's just now we don't have the diagram here. This is what's called a free body diagram. The other one's called a force diagram. You will get good at drawing these because I'm going to encourage you to always draw the picture. You probably have not, it's not the first time you've heard me say it. It won't be the last. But if you can draw a picture as to what's going on, you increase your chances of solving the problem by about 1,000%. So that's what we got to do there. Now, we're going to leave off there and we'll talk about the laws of motion here second. But when we come back tomorrow, we're going to practice drawing some of these and being able to figure out what is the total net force acting on the object. So that's all for today. Everybody have a great day. We'll see you later. Bye.